Tonight, I want to take you somewhere the universe becomes quietly unfamiliar. Not in the loud way science fiction imagines it, but in the soft, unsettling way reality reveals itself when you slow down and really listen to what the equations are saying. Because black holes are not just objects in space. They are places where space-time bends so deeply that ideas like distance, direction, and even before and after begin to lose their meaning. And once you accept that, a simple question follows. If space-time can curve into a black hole, is that the only extreme shape it can take? In this episode of Knowledge to Fall Asleep, 2, we'll gently explore what lies beyond black holes, white holes, wormholes, and the strange geometries that emerge when space-time is pushed to its limits. Not as science fiction, but as quiet possibilities written into the mathematics of the universe. So get comfortable, let your thoughts drift, and join me as we move slowly into the deepest curves of space-time. Black holes are among the most difficult things in the universe to truly understand, not because they are distant or rare, but because they are not objects in the way we usually imagine. A black hole is not a thing floating through space. It is the result of space-time itself being bent to an extreme. And when space-time is distorted this deeply, the universe begins to behave in unfamiliar ways. Motion no longer feels intuitive. Light does not follow the paths we expect. Time itself begins to soften, to stretch, to slow. Some of these effects are so strange that they seem almost unbelievable. Things you might doubt, if not for the quiet certainty of mathematics and the growing evidence written across the universe itself. Over time, observation after observation has gently confirmed what the equations once only suggested. Black holes come in many sizes. The smallest we've observed are only a few times more massive than our sun. And at the other end of the scale are ancient giants, black holes that formed when the universe was still young, carrying billions of solar masses within them. Some of these enormous black holes are so large that their surrounding boundary could easily contain our entire solar system. And yet, what lies at their center may be unimaginably small. The black holes forming today are born at the very end of a massive star's life. A star like this exists in a delicate balance. Gravity pulls its matter inward toward the center. At the same time, deep within the core, hydrogen atoms are pressed together with such force that they merge, becoming helium. This fusion releases energy, energy that flows outward as heat and light, gently pushing back against gravity's constant pull. For a long time, the star remains calm, stable, quietly shining. But eventually, the fuel begins to fade. As hydrogen runs out, the star turns to heavier elements, helium, then carbon, neon, oxygen, silicon, until finally iron begins to gather at the core. And iron changes everything. Fusing iron releases no energy. It gives nothing back. So the core grows heavier while the outward pressure disappears. Very quickly, gravity takes over. The star collapses inward with overwhelming force. Its outer layers crash down and rebound in a vast explosion, a supernova, one of the most powerful events the universe can produce. Matter and energy are hurled into space. Elements heavier than iron are formed, scattered across the cosmos, becoming the raw material of future worlds. What remains depends on the star's mass. If it is light enough, the core becomes a neutron star, a sphere no wider than a small city, yet heavier than 1,000,000 Earths. But if the mass is too great, even this extreme state cannot hold, and the laws of physics, as we know them, quietly begin to fail. What remains is a black hole. When you see an image of a black hole, the dark sphere you're looking at is not the black hole itself. It is the shadow cast by something far stranger. Yeah, scientists believe that the true shape of a black hole may be far smaller than it appears, even denser than a neutron star, perhaps compressed into something unimaginably tiny and heavy, a singularity where matter is packed so tightly that it distorts both space and time beyond anything we can directly observe. And yet, we don't truly know what exists there, because everything we might use to find out is stopped by something called the event horizon. Every object with mass creates gravity. This much has been understood since the time of Newton, but in 1915, when Albert Einstein introduced his theory of general relativity, gravity was no longer seen as a simple force. It became a bending of space-time itself. Soon after, one of Einstein's contemporaries, Karl Schwarzschild, realized that if enough mass were compressed into a small enough region, gravity could become so intense that not even light would be able to escape. And if even light, massless and fast, cannot get out, then nothing can. So when you look at an image of a black hole, you are not seeing the black hole itself. What you are seeing is the event horizon around it, the boundary where gravity becomes overwhelming, where light can no longer return, and where darkness remains. Not because nothing exists there, but because nothing can carry information back to us. But black holes do more than reshape space. They also change time. According to Einstein, space and time are inseparably connected, woven together into a single fabric, and mass bends that fabric. Near a black hole, as this bending becomes extreme, so extreme that the event horizon also marks the place where time itself appears to stop. For an outside observer, watching matter fall inward, something strange happens. As the object approaches the black hole, it seems to slow down, moving more and more gradually until just before reaching the event horizon, it appears to freeze in place. You never see it cross. There is no clear moment of absorption. Instead, the object slowly fades, its light stretched and weakened, until it disappears from view entirely. From the outside, nothing ever seems to fall in. When black holes were first proposed, many astronomers and physicists were unsure whether they truly existed or were simply mathematical curiosities. For decades, they remained theoretical. Then, in 1964, the first strong evidence appeared. Using newly developed X-ray satellites, scientists detected an intense source of X-rays coming from the constellation Cygnus. The strange thing was that no visible object could be seen there. If it were a normal star, it should have been shining brightly in visible light as well. The mysterious source was named Cygnus X1. By 1970, more advanced observations revealed that whatever Cygnus X1 was, it was orbiting a companion star. From that motion, scientists were able to calculate its mass, and what they found was unexpected. The invisible object was about 15 times the mass of the Sun, far beyond the upper limit for even the densest neutron stars. Quietly, the conclusion became clear. This was very likely the first black hole ever identified. Since then, many more have been discovered. Massive black holes appear to reside at the centers of galaxies, including our own. And in recent years, we've even captured images of their shadows. set against glowing rings of matter spiraling inward. Black holes themselves emit no visible light. The X-rays we detect come instead from their accretion disks, where infalling gas and dust are heated to millions of degrees by intense friction as they spiral closer and closer to the edge. Without this falling material, a black hole would be almost impossible to detect. Silent, dark, and invisible against the background of space. The study of black holes is still unfolding. With every observation, we learn a little more, and at the same time become more aware of how much remains unknown. And you might begin to wonder whether a black hole can ever stop being a black hole, or whether it will continue to grow forever, until there is nothing left in the universe for it to consume. However, in 1974, something unexpected entered the story. In a paper titled Black Hole Explosions, the physicist Stephen Hawking suggested that there might, in fact, be a way for energy, and therefore mass, to slowly escape from a black hole. At first, the idea seems almost impossible. To understand why it might be true, we have to step gently into some of the strangest territory in modern physics, into ideas drawn from quantum mechanics. But before we do that, it helps to pause and ask a deceptively simple question. What is nothing? Imagine for a moment a region of space completely empty. No atoms, no cosmic dust, not even radiation passing through. From everything you can see, it appears that nothing exists there at all. But is it truly empty? There is something subtle hiding in that apparent void, and we can sense it when a beam of light travels through it. Light, after all, behaves as a wave, an interwoven oscillation of electric and magnetic fields moving steadily forward. And when we hear the word wave, we tend to picture something familiar. A wave on the ocean, for example, is energy moving through water. If you watch a single droplet, it doesn't travel across the sea. It simply moves in a small circle, passing its energy to the next droplet and the next, until that energy finally reaches the shore. Sound works the same way. Air molecules barely shift from their positions, yet energy moves through them, carried from particle to particle, traveling outward while each individual piece moves only slightly. But in the vacuum of space, where there is no water and no air, light still travels as a wave. And this raises a quiet but unsettling question. If nothing is there, what is waving? This suggests that something fundamental exists, even in emptiness, an underlying structure that fills all of space and forms the backdrop of reality itself. Physicists call this structure a quantum field. Quantum fields are difficult to picture and even harder to fully understand, but they are essential to the story of what eventually happens to a black hole. Returning to Hawking's idea, he proposed that black holes are not perfectly sealed after all. Instead, they slowly release energy over time, in amounts so small that the process is almost imperceptible at first. And because energy and mass are simply two expressions of the same thing, as described by Einstein's famous equation, this gradual release of energy means a gradual loss of mass. At first, the change is unimaginably slow. But as the black hole loses mass and grows smaller, the process accelerates. The less massive the black hole becomes, the faster it releases energy until in its final moments, after timescales far longer than the current age of the universe, it releases a tremendous burst of radiation before disappearing completely. And this brings us back to the mystery. If the event horizon is truly unavoidable, If nothing can escape once it crosses that boundary, then how can radiation possibly get out? How can a black hole lose anything at all, let alone end in such a dramatic release of energy? That question remains one of the deepest and most fascinating puzzles in modern physics, resting at the fragile boundary between gravity, quantum mechanics, and our still incomplete understanding of the universe. The answer turns out to be very strange, rooted in ideas from quantum theory that feel deeply unintuitive, almost the opposite of how we experience the world in everyday life. And if this is true, then it helps to be prepared for the idea that the universe may be far stranger than it first appears. To begin understanding Hawking's theory, we need to gently introduce the idea of quantum fields. You may remember that light travels as a wave, even through regions of space that seem completely empty. This alone suggests that something must exist even in apparent nothingness, because without some underlying structure, there would be nothing for the wave to move through. Physicists call this hidden structure a quantum field. In fact, they believe that many different quantum fields overlap and fill every region of the universe, everywhere and at every time, past, present, and future. Each field corresponds to a particular type of particle. One field defines all electrons, another defines quarks, the building blocks of atoms. Where we think there is nothing, these fields are still there, quietly present. Most of the time, a quantum field is calm, like a guitar string that has not yet been plucked, or a graph resting at zero. But wherever energy or mass appears, the field begins to resonate. And when that resonance reaches a certain threshold, the universe expresses it as something tangible. An electron, a photon, a particle of matter. In this picture, the resonance is not merely reacting to matter, it is the matter. An electron is nothing more than a vibration in the electron field. The same is true for every particle, for all energy, and for all matter. As Einstein showed us, mass and energy are simply two forms of the same underlying thing. In this sense, everything you see around you, the stars, the planets, even yourself, is made of quantum fields quietly resonating. Seen this way, the universe begins to resemble a vast piece of music played across countless invisible strings. It's a poetic image, and one that turns out to be surprisingly accurate. But why does any of this matter? Why do we need to think about the universe in this way? The answer comes from a principle in quantum physics known as the Heisenberg uncertainty principle. Without diving too deeply into the mathematics, but this principle tells us that at very small scales, down at the level of atoms and particles, there are limits to what can be known. You cannot know both the exact position of a particle and the direction it is moving at the same time. The problem isn't that our instruments are too crude. It's that the universe itself does not allow such certainty. The moment you try to pin down the position of something as small as an electron, it is disturbed. And if you know where it is, you lose information about how it is moving. If you know how it is moving, its position becomes uncertain. This is not a flaw in measurement. It is a fundamental feature of reality. When this uncertainty is applied to quantum fields, things become even stranger, because these fields exist everywhere, and because they can never be perfectly still. They are constantly fluctuating, and according to the uncertainty principle, these fluctuations allow pairs of particles and antiparticles to briefly appear out of the field, exist, for an incredibly short time, and then vanish again. The details of how and why this happens are complex, but the essence is simple. The universe permits these brief appearances as long as they do not last too long. At first, this idea feels impossible. Matter should not simply appear from nothing. We never see this happening in our everyday world. And yet, there is evidence. In an experiment proposed by Hendrik Casimir, two conductive metal plates were placed extremely close together, so close that only certain types of quantum fluctuations could fit between them. Outside the plates, all fluctuations were allowed. Inside, many were excluded. This created a tiny difference in pressure, and that difference was enough to push the plates toward each other. The effect was real, measurable, reproducible. It showed that these quantum fluctuations, these fleeting particles appearing from the field, are not just mathematical tricks. They have physical consequences. You might worry that particles appearing like this would violate the conservation of energy, and in a sense they would if the universe didn't immediately balance the books. Whenever one particle appears, a second appears alongside it. One is matter, the other is antimatter. One counts as positive, the other as negative. Together, they add up to zero. The universe remains satisfied. Almost instantly, these paired particles meet, cancel each other out, and disappear again, leaving no lasting trace. This constant appearance and disappearance is why empty space usually feels empty, even though it is never truly still. Quantum fields are always vibrating, always balancing, always quietly erasing themselves. And it is within this restless, flickering background, this subtle activity beneath emptiness, that the fate of a black hole begins to change. But what happens if some of those resonances are no longer allowed to fully form? This is where black holes enter the picture. A black hole acts a bit like pressing your thumb against one of the universe's guitar strings. Because of the event horizon, some vibrations in the quantum fields are damped or cut off entirely, while others are not. The fields are still there, still present everywhere, but they no longer behave the way they did before. Hawking imagined drawing a single line through time at the location where a black hole forms. Along this line, a quantum field continues to exist, stretching from a time before the black hole was born into the far future after its formation. Before the black hole appears, everything behaves normally. Quantum fields resonate freely, fluctuations arise, and particle pairs cancel each other out as they always have. But the moment the event horizon forms, the curvature of space-time changes, both inside it and just outside. When Hawking followed the mathematics beyond that point, he noticed something subtle and unsettling. Some of the vibrations no longer had matching partners. Not everything was canceling out anymore. Far from the black hole, as you move outward, these leftover resonances take on a very specific form, one that looks exactly like thermal radiation drifting away into space. Radiation is energy, and energy cannot come from nothing. So if radiation is appearing outside the event horizon, the black hole must be paying the price. Every tiny fragment of what we now call Hawking radiation corresponds to an equally tiny loss of energy from the black hole itself. Over vast stretches of time, this loss adds up. If the process continues long enough, the black hole will eventually lose all of its mass. Hawking once compared it to money mysteriously appearing outside a bank, while at the same time, the amount locked inside the vault slowly decreases. The idea is elegant, but proving it is extraordinarily difficult. Hawking predicted that this radiation would be colder than the cosmic background radiation that fills the universe, and that its wavelength would be comparable to the size of the black hole's event horizon. For some black holes, that horizon can be as large as an entire solar system, making the radiation almost impossibly faint to detect. In practice, we would only expect to clearly observe Hawking radiation once the universe itself has grown cold and empty, when nothing else remains to overwhelm it. And by then, it is unlikely that anyone or anything will be around to observe it. Still, despite these challenges, the mathematics remains consistent. And intriguingly, Hawking radiation appears to have an unexpected cousin: sound. In recent years, scientists have taken creative steps toward testing Hawking's ideas in the laboratory by building analog systems, what are sometimes called sonic black holes. These experiments take advantage of the fact that sound moves far more slowly than light, making it much easier to create regions where motion exceeds the speed of sound. In such a setup, sound waves traveling in the same direction can no longer escape, creating an acoustic event horizon. Remarkably, when Hawking's equations are applied to these sonic black holes, they predict the same kind of radiation, and that radiation has been observed. After repeating the experiment tens of thousands of times over months of continuous testing, researchers detected signals that matched Hawking's predictions with striking accuracy. While this does not prove that Hawking radiation must exist around real gravitational black holes, it offers strong evidence that the underlying mathematics may indeed be describing something real. Hawking radiation may not just be a theoretical curiosity. It may be a genuine feature of the universe. So if you were to fall into a black hole, could you escape? Probably not. But if you were willing to wait until the very end of the universe, until the black hole slowly evaporates through Hawking radiation, then piece by piece, the mass and energy that once made you up could eventually be released from within the event horizon. Does that count as escape? Perhaps not in any way you would find comforting. It's probably best not to go in at all. And yet, a black hole's hint at something even stranger, something unsettling about the nature of reality itself. When you walk along a beach and leave footprints in the sand, there is no doubt about what caused them. Your feet made the prints. The prints did not make your feet. Cause and effect seem obvious. So obvious that it feels almost absurd to question it. But what if that relationship were more complicated than it appears? What if, on a cosmic map, the connection between cause and effect were not always so clear? Surprisingly, the existence of black holes and Hawking radiation suggests that this might be the case. To begin exploring this idea, we need to step back and consider a principle known as relativity. But not Einstein's relativity just yet. Instead, we start with Galilean relativity, first described by Galileo Galilei in 1632. The basic idea is simple. There is no absolute difference between being perfectly still and moving at a constant speed. Imagine two sealed rooms with no windows, one sitting quietly on land, the other inside a ship moving smoothly across a calm sea. From inside either room, with no reference to the outside world, could you tell which one is moving? You might feel like you could, but you can't. Right now, as you sit where you are racing through space at about 110,000 kilometers per hour as Earth orbits the sun. and yet you feel completely still. Galileo realized that no experiment performed inside the room could distinguish between rest and constant motion. If you dropped a ball inside the moving ship, it would fall straight down from your perspective, even though someone watching from the shore would see it follow a diagonal path. Remove all external reference points, and motion becomes relative. In empty space, there is no way to tell whether you are moving toward a planet or the planet is moving toward you. Both descriptions are equally valid. You may have noticed this yourself while sitting on a train, when another train suddenly begins to move beside you. For a moment, it can feel as though you are drifting backward, even though you are still moving forward, because your frame of reference has shifted. Einstein would later take this idea much further, developing it into the principle of equivalence. And that is where the story becomes even stranger. Here, Einstein returned to the idea of the two rooms, but this time he was thinking about gravity. Imagine you are inside a windowless room, drifting freely through the vacuum of space. Now imagine that someone attaches a rocket to the bottom of the room and begins to accelerate it upward. If the acceleration is smooth and steady, the experience inside the room would feel exactly the same as standing on the surface of Earth. You would feel your feet pressed against the floor. Objects would fall downward. Everything would behave as if gravity were present. In other words, there is no way to distinguish between acceleration caused by gravity and acceleration caused by a rocket, so long as you have no outside reference and the motion remains smooth. Both situations rely on the same underlying idea: inertia. Objects prefer to keep doing whatever they're already doing. They do not like to change their motion. If something is at rest, it will remain at rest. If it is moving, it will continue moving unless a force intervenes. So why does the person in the accelerating room feel as though gravity is pulling them downward? And perhaps more strangely, why do we, standing on Earth, feel as though we are being pushed upward? The Earth is not expanding beneath our feet, pushing us up the way a rocket would. And yet, the sensation feels the same. Einstein realized that this similarity was not a coincidence. In both cases, what you are experiencing is acceleration. But there is another kind of acceleration that helps clarify how gravity truly works. Acceleration caused not by being pushed, but by being forced to change direction. Think about a carnival ride that spins in a circle. When you lean against the wall of the ride, you feel a strong force pressing you outward, even though the ride is moving at a constant speed. The reason is that your body is constantly trying to move in a straight line, while the curved path of the ride forces you to change direction again and again. The sensation you feel is the result of a struggle between your inertia, your desire to keep moving straight, and the constraint of the curved path. Einstein realized that gravity behaves in a similar way. Rather than being a force that pulls objects downward, gravity can be understood as the result of motion through curved space. Matter and energy distort the space around them, much like a heavy ball placed on a stretched rubber sheet. The greater the mass, the deeper the curvature. And once space is curved, objects moving through it naturally follow those curves. As the physicist John Wheeler famously put it, space-time tells matter how to move, while matter tells space-time how to curve. For small masses, the curvature is gentle. For For extremely large masses, it can become so steep that anything moving too close can no longer escape. These are the conditions we find near a black hole and its event horizon. So returning to our earlier metaphor, if a black hole is the foot, then the curvature of space around it is the footprint. Up to this point, nothing here is especially strange. Understanding the mechanism does not make gravity feel more mysterious. Space curves. Objects move along those curves. Everything behaves exactly as our everyday intuition would suggest, just on a much grander scale. But when we introduce Hawking radiation, something deeply unsettling happens. The most important thing to understand, at least for now, is that Hawking radiation is not local. It does not emerge from the black hole itself. It does not come from the singularity, nor even directly from the event horizon. The black sphere you see in images is simply the boundary between escapable and inescapable curvature. Space, as we understand it, does not meaningfully exist beyond that boundary. And despite how Hawking radiation is sometimes described, it does not arise from pairs of particles popping into existence right at the edge, with one falling in and the other escaping. That picture is a helpful metaphor, but it is not what is actually happening. Instead, the region where Hawking radiation can form is vastly larger than the event horizon itself. It can extend billions of kilometers into surrounding space. For the largest black holes, whose event horizons could contain multiple solar systems, this means that Hawking radiation may appear incredibly far from the black hole, well outside the boundary we usually imagine, which is strange enough on its own. But stranger still is that it appears in a place where, by every ordinary definition, there is nothing at all. In essence, Hawking radiation does not come from the black hole. It comes from the curvature of space created by the black hole. And that curvature can produce radiation far away from the source itself. If that is true, then everything works in reverse. As energy leaves the curved space-time around the black hole, the curvature must decrease in accordance with the conservation of energy. And as the curvature decreases, the black hole itself shrinks. It is as if the footprint was shrinking and the foot followed. It feels wrong, intuitively backward, and yet Einstein's equations quietly allow for exactly this possibility. In them, the curvature of space-time is proportional to the energy and mass present, but proportionality does not imply causation. The equations never say that mass must come first and curvature second. We are accustomed to thinking that changing mass changes curvature. But what if changing curvature changes mass? If that were true, it would suggest a universe in which mass itself is not fundamental, but instead a projection, a shadow cast by something deeper happening in the geometry of space-time. When you shine a light on your hand and see a shadow on the wall, the shadow exists because of the hand. And it feels natural to assume that we are the hand, that our mass creates the curvature around us. But how do we know it doesn't work the other way around? What if we are the shadow? What if matter, energy, and even ourselves are projections, patterns formed by something more fundamental unfolding within the curvature of space-time itself? And yet, we go on believing that we are the real thing. The truth is, we don't really know. All you ever have access to is the reality you experience from the inside. And because of that, it becomes almost impossible to distinguish between these possibilities. And if relativity has taught us anything, it is this. when there is no experiment that can clearly separate two situations, then we cannot completely rule out that either of them might be true, or that both are somehow part of the same deeper picture. Of course, all of this remains speculative. There is still no direct proof that Hawking radiation exists around real black holes, even though some experiments hint in that direction. But even if reality did turn out to be some kind of projection or reflection, it would likely change very little about your daily life. You would still think, you would still feel, and that alone would be reason enough to keep going. And yet, these ideas matter, because when we begin to examine the most fundamental building blocks of reality by following the strange distortions caused by black holes, we are sometimes forced to question assumptions we rarely notice we are making about ourselves. Asking, am I real? And arriving at the answer, I'm not entirely sure, is unsettling. Black holes affect our universe not only because they pull in everything that comes too close, never to return, but because they seem to represent an endpoint, a final sink where matter, energy, and information disappear. And yet, what if that isn't the whole story? What if black holes are not only destroyers, but also, in some sense, a form of salvation? What if they offer clues to travel beyond ordinary limits, beyond the speed of light, or to solving energy problems in ways that, until recently, we could not even imagine? As strange as it sounds, they do this not by obeying our expectations of physics, but by quietly undermining them, by interfering with the very structure of reality itself. Perhaps we have been thinking about black holes in the wrong way. To understand how a black hole might bypass the usual limits on motion faster than light, without ever needing to cross its event horizon, and how it might generate almost unimaginable amounts of energy at the same time, we need to look more closely at what black holes are allowed to be. And here we run into a familiar obstacle. It is difficult to say much about the internal properties of a black hole, precisely because of the event horizon. We cannot see inside. We cannot receive signals from within. And so, remarkably, there are only three things we can say about a black hole with any real certainty. A black hole has mass. It can carry electric charge, and it can spin. It has angular momentum. You might wonder how we can know even this much, when no light ever escapes to tell us what's happening inside. The key is that all three of these properties affect the universe outside the event horizon. They leave measurable fingerprints in the surrounding space. Take electric charge, for example. A charged black hole behaves at its event horizon much like any other charged object. It attracts objects with opposite charge and repels those with the same charge, influencing the motion of particles nearby. You can imagine it like a vast invisible magnet, subtly pulling and pushing the space around it. By carefully tracking how charged particles move as they approach a black hole, scientists can infer the black hole's charge, even without seeing the black hole itself. Mass works in a similar way. The mass of a black hole can be felt far beyond its event horizon, and in fact, it is mass that creates the event horizon in the first place. Mass generates gravity, and it does so in a predictable, linear way, following principles similar to those found in Gauss's law in electromagnetism. By observing how nearby objects begin to accelerate, how fast they move, and at what distance this acceleration becomes noticeable, scientists can calculate the mass of the black hole, so long as they account for the effects of charge at the same time. These measurements are indirect, careful, quiet. But they are enough to tell us that black holes, though hidden, are not completely unknowable. They influence the universe around them in subtle, measurable ways. And through those influences, they continue to whisper clues about the deeper structure of reality itself. The final property we can speak about with any confidence is angular momentum, spin. The rotation of a massive object leaves signatures that can be detected from the outside, and we'll return to how that works shortly. For now, it's enough to accept one simple fact. Black holes are extraordinarily massive objects, and like most things in the universe, they can rotate. Black holes come in many different sizes. The smallest theoretical kind, sometimes called micro black holes, could have a mass comparable to that of our moon, yet contain all of that mass within a space only fractions of a millimeter across. Something thinner than a human hair, holding the mass of the moon, gives a sense of just how extreme black hole density can be. Stellar black holes are larger, often carrying around 10 times the mass of the sun within a region only tens of kilometers wide. Intermediate black holes scale up further, packing thousands of solar masses into a volume still smaller than Earth. And then there are the giants, the supermassive black holes at the centers of galaxies, ranging from hundreds of thousands to billions of times the sun's mass, with sizes stretching from fractions of an astronomical unit to hundreds of them. And yet, beyond these three measurable properties, mass, charge, and spin, there is, in theory, no difference between black holes at all. If you placed two black holes in the same room and ensured they had identical mass, charge, and rotation, there would be no experiment you could perform to tell them apart. They would be, for all external purposes, the same object. These three properties alone, however, are enough to produce a remarkable range of effects in the space surrounding a black hole. What happens inside remains inaccessible. Space and time, as we understand them, lose their meaning beyond the event horizon. Still, we believe something must exist there. At the center of every black hole is thought to lie a singularity, the true black hole itself. The sizes we usually talk about are only the sizes of the event horizon, not the object at its core. We don't know what a black hole truly looks like inside because no light can ever escape from that region. All of its mass appears to be compressed into an unimaginably small volume, creating densities that push our current theories to their limits. In the simplest models, or non-rotating black holes, the singularity is treated as a single point. In rotating black holes, it behaves more like a tiny spinning ring. Trying to define spin for something with no volume quickly leads physics into strange territory. Certain idealized paths through this region allow for mathematically bizarre possibilities, such as encountering your own past, which raise serious problems for causality and lead to classic time travel paradoxes. This doesn't mean those paradoxes are real. It almost certainly means our understanding is incomplete. To truly describe what happens inside a black hole, we would need a theory that successfully unites quantum mechanics and general relativity. We don't yet have such a theory. It may turn out that singularities do not exist at all, and that something else replaces them at the core. For now, this is simply the edge of our knowledge. Whatever lies inside, however, its power is one of the most extraordinary features of black holes, their rotation. As you move outward from the center, the rotation becomes more pronounced. And although crossing the event horizon itself produces no dramatic local signal, no trumpet blast, no sudden sensation, its consequences are profound. From the perspective of an outside observer, you would appear to slow down and freeze at the horizon. From your own perspective, time would continue to flow normally, even as the universe outside races toward its distant future in what feels like a brief moment. This is relativity at work. The only local clue that you have crossed the event horizon comes from something just outside it, the photon sphere. In a narrow region surrounding a black hole, there exists a place where light itself can orbit. A photon entering this region at exactly the right angle can circle the black hole endlessly, much like the moon orbits Earth. Over millions of years, countless photons may accumulate there, making it an intensely energetic and likely deadly place to pass through. Just beyond this lies the region of real interest, the black hole's atmosphere. This is where the rotation of the black hole becomes impossible to ignore. Mass does not merely curve space, it drags it. As a massive object rotates, it pulls space-time around with it, an effect known as frame dragging. In simple terms, reality itself begins to swirl. Anything caught in this region is forced to rotate along with the black hole, not because it is being pushed, but because the very frame of reference it occupies is moving. It's like standing on a moving walkway. Even if you try to remain still, you are carried along. The faster the black hole spins, the stronger this effect becomes. Near the event horizon, space-time can be dragged so rapidly that it moves faster than the speed of light relative to distant observers. To remain stationary, you would need to move faster than light in the opposite direction, which, of course, is impossible. Does this violate Einstein's rules? No, because the rule that nothing can move faster than light applies locally within your own frame of reference. Relativity allows frames of reference themselves to move apart at extraordinary speeds. If you were to enter such a frame, everything would once again behave normally. Frame dragging is not just theoretical, it is real, and by measuring it, scientists can determine how fast a black hole is spinning. But according to the physicist Roger Penrose, it might also be usable. If a spacecraft were sent into this rotating region, it would be accelerated by the swirling space-time itself. At the right moment, it could eject part of its mass in such a way that it escapes the vortex, carrying far more energy than it entered with. This process, known as the Penrose process, could, in theory, convert up to 20% of the spacecraft's mass into usable energy. 20% may not sound like much, but remember Einstein's equation. Converting even a fraction of mass into energy yields an almost unimaginable amount of power. In practice, this would require traveling thousands of light years to a nearby black hole, approaching its atmosphere without being destroyed, and finding one without a blazing accretion disk hot enough to melt matter into plasma. So yes, it is wildly impractical, but the implication is profound. Black holes hint at a way of exceeding ordinary limits, not by moving faster than light ourselves, but by persuading space-time itself to move faster around us. If such effects could ever be controlled, they might point toward entirely new forms of travel and energy. For now, this remains speculation. But once again, black holes remind us that the universe is not obligated to match our expectations. It is quieter, stranger, All of this, once again, reminds us just how different the universe truly is from what we instinctively imagine it to be. And here is another quiet surprise about black holes, one you might not expect at all. Falling into a black hole is far more difficult than it seems. You might assume it would be easy. After all, black holes are often described as the ultimate sinks, the strongest gravitational objects in existence. Surely nothing should be easier to fall into than a black hole. It feels obvious. And yet, that intuition is wrong. In fact, supermassive black holes are among the hardest places in the universe to actually enter. So much so that, for much of his life, Einstein himself believed that nothing could ever truly fall inside one. Stranger still, under the right conditions, a black hole can even fling matter away from itself at speeds approaching that of light. This seems completely backwards. Shouldn't a black hole behave like an ever-steepening slide, pulling you faster and faster the closer you get? And in one sense, that is true. You do accelerate. Your speed increases, far approaching the speed of light. But in most realistic situations, you will not find yourself getting significantly closer to the center at all. And this has nothing to do with time dilation or relativistic illusions. It is something that can be described in any reference frame. Confusing? That's okay. Let's ground it in something real. To understand why this happens, we need to talk about accretion disks. At their core, black holes are remarkably simple objects. According to what is known as the no-hair theorem, black holes have almost no distinguishing features. They are defined entirely by mass, charge, and spin, and nothing else. An accretion disk is not an inherent part of a black hole at all. A black hole can exist perfectly well without one hidden in darkness, completely invisible. Accretion disks only form when something unfortunate wanders too close. A star, for example, may stray into the black hole's gravitational influence and be torn apart by immense tidal forces. But here's the strange part. That material does not fall straight in. Instead, it spreads out into a thin, rotating disk orbiting just outside the event horizon. And although all of that matter will eventually fall into the black hole, the process can take an astonishingly long time, sometimes hundreds of millions or even billions of years. So what's stopping it? The answer lies in one of the most fundamental principles in physics, the conservation of momentum. Very simply, the total momentum of a system must remain constant. Momentum cannot be destroyed, it can only be transferred. A rocket sitting motionless on a launch pad cannot lift off unless it expels fuel downward. The upward momentum of the rocket is exactly balanced by the downward momentum of the exhaust. Nothing comes from nowhere. This principle feels counterintuitive only because we usually ignore the larger system. When you walk forward, you push backward on the ground. The ground pushes forward on you. The momentum is shared. You just don't notice the earth moving because it is so massive. Now let's extend this idea to angular momentum. Picture a ballet dancer spinning with their arms stretched wide. When they pull their arms inward, they spin faster. Nothing magical is happening. The angular momentum of the system is being conserved. The mass in their arms is now closer to the axis of rotation. So to maintain the same momentum, the rotation speed must increase. The same thing happens on a cosmic scale. Matter falling toward a black hole almost never approaches in a perfectly straight line. There is always a slight offset, a sideways motion, which gives the matter angular momentum. As gravity pulls it inward, it begins to spiral, orbiting closer and closer to the black hole. As the orbit shrinks, the rotation speed increases, just like the dancer pulling in their arms. But unlike the dancer, this matter faces an absolute limit. Nothing in the universe can move faster than the speed of light. Eventually, the orbiting matter reaches a point where it cannot spin any faster without violating that limit. It has hit a barrier, and once it cannot spin faster, it cannot fall inward any further. The result is friction. Near the edge of the event horizon, as matter in the accretion disk slams into itself at incredible speeds. Particles collide again and again, and at velocities approaching the speed of light, these collisions generate enormous heat. Temperatures can reach tens of millions of degrees, hot enough to strip atoms apart into glowing plasma. As this happens, energy is squeezed out of the matter. Between 10 and 40% of an atom's mass can be converted directly into energy and radiated outward into space. For comparison, nuclear fusion in the sun converts only about 0.7% of mass into energy. Pause on that for a moment. The sun shines as brightly as it does with less than 1% efficiency. Now imagine a system converting tens of percent of its mass into pure energy. This is why accretion disks can outshine entire galaxies. The brightest of them, known as quasars, can emit more light than all the stars in the Milky Way combined. Eventually, the matter must lose angular momentum to fall any further. Some of it does this by transferring momentum outward, colliding with slower moving material above the disk. Some of it sheds momentum through one of the most dramatic features associated with black holes and quasars. They're jets. And that is where things become even stranger. We still don't fully understand these jets, how they form, what exactly they're made of, or why only a small fraction of black holes with accretion disks ever seem to produce them. But the leading ideas suggest they're driven by magnetic forces generated by the spinning disk and possibly amplified by the spin of the black hole itself, as if rotation and magnetism together create a kind of cosmic engine that can grab material from the disk and fling it outward into space. One way to picture it is to imagine the accretion disk as a vast charged current. Countless particles carrying electric charge, moving at extraordinary speeds, and whenever charges move, magnetic fields arise. So the faster and more organized the motion becomes, the more structured the field can become as well. Under the right conditions, those magnetic field lines can shape the chaos into something narrow and directional, leaving what looks like a channel along the black hole's poles, north and south, through which matter can escape, not as a gentle leak, but as a focused, collimated blast. The field can behave like the spiral grooves inside a gun barrel, guiding particles into a tight beam. And once matter is trapped in that channel, it has very few options left except to go where the geometry and the fields allow it to go. And still, even with that picture, there's a quiet honesty we have to keep. We don't fully know why it becomes that direction, that structure, that kind of outflow. Sometimes it helps to imagine something more familiar, something almost domestic, like steam in a kettle, because even there, the pressure doesn't escape everywhere at once. It escapes through the one opening that exists. And once it finds that opening, it commits to it completely. These relativistic jets can travel astonishing distances, stretching far beyond the galaxies that launch them. sometimes reaching for millions, perhaps even billions of light years. And although the light that reaches us can be faint, we can still detect it across immense cosmic time because the radiation in a jet is not spread evenly in all directions. It is concentrated forward, tightened into a beam by relativistic effects, like a lighthouse whose light is brightest only when it sweeps across your eyes. When the beam points toward us, the jet can appear dramatically brighter and easier to study. When it points away, it can become frustratingly difficult to observe, even if it's equally real. This is part of why some famous systems feel one-sided. In galaxies like M87, for instance, we can clearly see a jet on one side, and it's very likely there is another pointing the other way. But it is either dimmed by geometry or simply not aimed in a way that makes it visible to us. And it's worth saying again, because it's easy to forget in the drama of the image that none of this energy is coming from inside the black hole. Nothing escapes the event horizon. The jets, like the brilliant light of quasars, arise from the environment around the black hole, from the accretion disk, from magnetic fields, from rotation, from the violent conversion of motion into heat and radiation. Even so, much of what we say about jets is still theoretical. We can see them. We can track changes in them over time. We can measure their enormous scales. But the exact mechanism that launches and stabilizes them, and the deeper accounting of where all the angular momentum ultimately goes, is still not fully settled. Accretion disk physics explains a great deal, but not everything. And there remains a kind of unresolved whisper in the equation, a sense that something about the full momentum budget is still hiding in the details. What is undeniable is the power. Einstein may have been wrong about black holes being impossible to enter. Clearly, matter can fall in. But when some black holes also hurl matter outward at near light speed across distances that can dwarf the size of their own galaxies, it becomes equally clear that falling in is not the only story. Add to that the brutal outward pressure of million-degree plasma trying to rid itself of angular momentum, and you begin to understand why getting close to an active black hole is not just difficult, but something you might not want to do at all. So we've seen that a black hole's influence can reach across a galaxy, not only through gravity, but through light, the heat, radiation, and jets that carve through intergalactic space. And that naturally leads to another question, one that feels almost inevitable once it appears in your mind. How large can a black hole really become? In a sense, finding the biggest ones is not difficult conceptually. You look to the hearts of the largest galaxies. Supermassive black holes have had billions of years to grow, fed again and again by gas, dust, stars, and the slow rain of matter drifting inward, and the largest among them can reach masses of billions of suns. But here, the universe offers another surprise. Some of the largest black holes we know about appear in the distant universe, so distant that we are seeing them as they were when the cosmos was still young. And because looking far away is the same as looking back in time, this creates a strange tension in the story. If these objects were already enormous so early, how did they grow so quickly? One famous example often discussed is a quasar called TON 618, estimated to host a black hole tens of billions of times the mass of the sun. It is extraordinarily far away, so distant that the light we receive from it began its journey billions of years ago, meaning we see it as it existed in a relatively early chapter of cosmic history. And yet, when we compare this to the supermassive black hole in the Milky Way, Sagittarius A star, only a few million solar masses, or even to the one in Andromeda, which is larger but still nowhere near that scale, it can feel as though the distant universe is somehow hiding the giants, while the nearby universe is, by comparison, almost modest. But part of the answer is simple and humbling. Black holes are hard to detect, and the tools that let us study them directly are still young. For decades, we could only infer black holes by their effects on nearby stars and gas. And even now, even with instruments like the Event Horizon Telescope producing historic images, it can take immense effort to capture even a single target. Our census of black holes, especially the faraway ones, is still incomplete. And what we think we know is shaped by what we are able to see. And what we are able to see from the farthest distances is often dominated by quasars. TON 618 is a quasar, an active black hole whose accretion disk is being fed at such extreme rates that the disk becomes one of the brightest beacons in the universe. Quasars remain quasars only as long as matter continues to fall in, or when the feeding slows, the blaze fades, and the black hole becomes dark again, blending back into the background of space. The physics inside an accretion disk is difficult to hold in the mind all at once, but the idea is straightforward. Friction and turbulence can be so intense that the disk itself can outshine the entire galaxy that hosts it. In some of the brightest cases, the quasar's glare is so overwhelming that the galaxy becomes almost invisible behind its own central light, like a candle held in front of a faint landscape. And because quasars are among the brightest objects in existence, they can be seen from much farther away than normal galaxies. This leads to a selection effect. When we look to the deep universe, the objects that dominate our view are the brightest ones, while the dimmer ones, perhaps equally common, simply fall below the threshold of detection. This is often discussed in astronomy as a form of Malmquist bias. Far away, brightness strongly influences what makes it into our catalogs. So the distant universe can appear to contain more extreme objects simply because the extreme ones are the easiest to see. Which means it is entirely possible that enormous supermassive black holes are not rare at all, but more evenly distributed than our limited view suggests. If a nearby galaxy hosted a giant black hole that was quiet, no quasar, no bright accretion disk, then beyond some distance we might never notice it, because a normal galaxy is far dimmer than a quasar, and the signature would be too subtle to pick out. There is another, and a deeper reason the early universe can feel so quasar-rich. In the youth of the cosmos, matter was packed more closely together. There was more available gas, more dense environments, more frequent feeding, and quasars thrive on abundance. Over time, the universe expanded, and much of the gas that once floated freely was gradually locked away into stars, and then into stellar remnants, neutron stars and the black holes, which are not easily recycled back into the diffuse gas that feeds galactic centers. As the universe ages, the easy fuel becomes rarer. Less available gas means fewer galaxies in the bright active phase that makes black holes obvious to us. Some galaxies, in fact, have used up or expelled so much of their gas that they can no longer form new stars at all. These are often the smooth, quiet, elliptical galaxies, older, redder, the more settled, while spiral galaxies still retain enough gas and dust to keep forming new stars, still carrying a kind of ongoing motion and unfinished chemistry through their arms. And all of this, jets, quasars, the fading of gas with cosmic time, begins to hint at a much larger destiny, one where the universe slowly trades its bright, living complexity for darker, simpler endings. But that, too, is a story we have to approach gently, because the deeper you follow black holes, the more the universe starts to feel like it is thinking, in a language we are only just beginning to learn. It's also quietly telling that many of the most massive, supermassive black holes seem to live in elliptical galaxies, galaxies that have already gone still, where the cold gas has largely disappeared. Gas can't simply fall straight into the central black hole. It has to lose angular momentum first. It has to give up that sideways motion that keeps it circling, and when a galaxy manages to drain that angular momentum efficiently, the black hole at its core can grow far larger, fed over long stretches of time by the material that finally succeeds in sinking inward. In elliptical galaxies, that draining has largely already happened. In spirals like the Milky Way, it hasn't happened to the same degree. And one of the most effective ways to steal angular momentum from gas is gravitational disturbance, nearby galaxies tugging on it, tides stretching it, or full collisions and mergers that scramble orderly orbits into chaos and let matter fall inward. Add to that the simple fact that the modern universe contains less available gas than the early universe did, and you start to see a pattern. Growth may have been fast when the cosmos was young and crowded, and slower now as the universe expands, thins out, and settles. This helps explain why active quasars are rare in our local cosmic neighborhood. Within a few 100 million light years, we don't see the same blazing abundance of quasars we see in the deep universe, because as time passes, galaxies become calmer, gas becomes harder to gather, and the quasar phase becomes less common, which means many of the quasars we do see, the ones that dominate our catalogs and our imagination, are often ancient light from objects that were active long ago, when conditions were more favorable. So why do the biggest black holes sometimes seem like the youngest? They might not be. It can look that way because the faraway universe is the universe we can only see through its brightest beacons. A quasar shouts across billions of light years. A quiet galaxy whispers, and beyond a certain distance, we simply can't hear it at all. This is the heart of the selection effect astronomers talk about. The bright things overpopulate our view of the deep cosmos, not necessarily because they are truly more common there, but because brightness determines what survives the journey into our telescopes. Older, nearer black holes could be enormous too, and if they're not actively feeding, if they're not wrapped in a luminous accretion disk, then they may be far harder to find than we'd like to admit. And as surveys deepen and instruments improve, the picture will likely change. The universe usually does that to us. It waits until we think we've understood the pattern, and then it reveals the parts we were never equipped to see. We've spent so much time with black holes because they are the most extreme distortions of space-time we know, regions where curvature is pushed close to its limits, where familiar intuition built from everyday Earth physics stops being useful. But black holes may not be the only way space-time can bend itself into something extraordinary. In theory, there may be other structures, other shapes, that fall out of the same mathematics. One of them is called a white hole, named that way because, in many respects, it is the mirror opposite of a black hole. And in some mathematical descriptions, a black hole and a white hole can be connected by something even stranger, a wormhole, a kind of bridge-like region of space-time that, at least on paper, can link distant places, or even different universes within an extended solution of Einstein's equations. If that sounds like science fiction, you're not wrong to feel skeptical. There is no observational evidence that white holes or traversable wormholes exist in our universe. But it's worth remembering that black holes once lived in that same category too. Pure theory, an unsettling implication of equations, until the evidence began to pile up, and the universe quietly admitted, yes, these things are real, and there are far more of them than you ever expected. So in this story, we're going to hold 3 questions gently in our hands. What other extreme forms of space-time might be possible? Is it reasonable to hope they could be more than fiction? And if they were real, what would they actually look like? Before we go deep into the full geometry of general relativity, it helps to start with a small, almost innocent analogy. If I ask you to picture a cone, you probably imagine a single shape, like a traffic cone or an ice cream cone. One point, one widening body, one direction. But if you write down the most general mathematical description of a cone and graph it, what you get is not one cone, but 2. One opening upward and one opening downward, joined at the tip. The cones we meet in ordinary life are often just pieces of the full mathematical object. And black holes can be like that. The black holes we talk about in astronomy usually form at a definite moment in time, when a massive star collapses and an event horizon appears, sealing off a region of space-time from the rest of the universe. In that familiar picture, light can fall in, but it cannot escape. Matter can cross the horizon, but it cannot return. The interior leads inevitably toward the singularity. Physicists often summarize this with something called a Penrose diagram, a way of compressing an infinite space-time into a finite drawing while keeping the causal structure intact. In these diagrams, light always travels at 45 degrees, which makes it easier to see what can influence what can reach what, and what is forever out of contact. In the simplest diagram, there's an ordinary region that represents the universe outside, stretching from the infinite past to the infinite future. There is a region representing the black hole interior, separated by the event horizon. And when you trace light rays, you see the defining feature of a black hole made visible in a single glance. Light can go in, but it cannot come out. And inside, the future points toward a singular end. But that common diagram, useful as it is, may be only a piece of the full mathematical story. If you stop thinking about realistic messy stars and instead imagine an idealized black hole with an eternal past, the equations allow an extended space-time that contains more regions than the simple formation diagram shows. Alongside the black hole region, the mathematics also describe something that looks like it's time reversed. A region you cannot enter from the outside, but from which light can emerge. A place with a singularity in the past rather than the future. A one-way boundary in the opposite direction. That is the essence of a white hole. And beyond that, the extended solution can include another asymptotically normal region, another Universe like space that is causally disconnected from ours, separated not by distance in the usual sense, but by the structure of space-time itself. In the full extension, the same equations that describe our external universe and a black hole also describe a white hole and a parallel external region, even if the physical universe only ever realizes part of that mathematical structure. This does not mean that every black hole we observe is connected to a real white hole in the sky. It means something quieter. White holes are not forbidden by the rules of the theory. They are allowed shapes in the same way the other half of the mathematical cone is allowed, even if the physical world tends to give us only the ice cream cone and rarely, if ever, the traffic cone. And that may be the key point. Perhaps white holes are unstable, perhaps they collapse, perhaps they erase themselves almost as soon as they appear, leaving no easy signature for us to find. Their absence would not make them unscientific. It would simply mean the universe does not favor them for long. But if you're wondering whether there could be forms of white holes that are smaller, subtler, harder to recognize, forms we might have missed, you're not alone. And to get there, we have to take one more step deeper into the geometry. So far, the diagrams we've discussed describe the simplest kind of black hole, non-rotating and uncharged. But real black holes spin, and spin changes everything. The Penrose diagrams for rotating or charged black holes become more elaborate, almost labyrinthine, and introducing new horizons and repeating structures that look mathematically like an infinite pattern of connected regions. In the idealized rotating case, the story inside is no longer a simple one-way fall toward an unavoidable future singularity. Beyond the outer event horizon, the geometry can include an inner horizon as well. And in those deep interior regions, the equations permit motion that feels less terminal than you would expect. In the most literal reading of the mathematics, there are paths that seem to avoid immediate destruction, paths that can loop around the ring-shaped singularity, and paths that appear to lead into other regions of the extended space-time. This is the point where the story becomes both thrilling and suspicious at the same time. Because these same idealized paths can also allow the kinds of causality problems that make physicists uneasy. Closed time-like curves, time travel-like loops, paradoxes that threaten the basic idea of cause and effect. The fact that the math permits them does not mean nature does. It may be a sign that the idealized solution is too perfect, that real black holes, formed in violent asymmetric collapse, surrounded by matter evolving over time, do not preserve the fragile conditions needed for those exotic passages to exist. And there's a second reason to be cautious. The Penrose diagrams are built from classical general relativity, and general relativity is almost certainly incomplete in the regime where curvature becomes extreme, near what we call a singularity. Quantum effects should matter. Without a complete theory of quantum gravity, some of the most dramatic features of these diagrams may be artifacts of pushing an incomplete framework beyond its rightful limits. So we return, gently, to reality. Even if wormhole-like structures appear in idealized mathematics, a real traveler would almost certainly not survive the environment, and the wormhole itself, if it existed, might collapse as soon as anything disturbed it. Still, the fact that the mathematics opens these doors at all is part of what makes black holes so unsettling. They hint that space-time has more possible shapes than the universe has shown us so far. Which brings us back to white holes, not as fantasy portals, but as a serious open possibility. One modern idea that has drawn attention is surprisingly poetic in its symmetry. Perhaps white holes are born when black holes die, not in a mystical sense, not as reincarnation, but as an attempt to complete the life cycle implied by Hawking radiation and quantum gravity. Even an isolated black hole should slowly lose mass via Hawking radiation, shrinking over unimaginable timescales. But once a black hole approaches the Planck scale, when it becomes so small that our current physics can no longer reliably describe what happens next, we are forced to admit we don't know the ending, at least not without a successful theory of quantum gravity. This is where approaches like loop quantum gravity enter the conversation. In that framework, space-time itself is not infinitely smooth, but built from discrete quantum structure. And in some loop quantum gravity-inspired models, the black hole does not continue shrinking into nothing. Instead, it can undergo a quantum bounce, tunneling into a white hole-like state. The exterior might remain tiny, but the interior geometry can be stretched into a vast volume like a long, thin pocket of space-time holding an enormous amount of information. And if something like that were true, it could offer a route, at least in principle, for information that fell into the black hole to be released again in the far future, addressing the black hole information problem that has haunted theoretical physics for decades. The white hole would then slowly fade as the curvature relaxes and the last traces of the process dissipate, bringing the life cycle to a close. And before we end, there's one final thought that lingers. In classical general relativity, our universe itself appears to have emerged from a singular state in the past, what we call a Big Bang. In that sense, the universe resembles a kind of white hole-like beginning, a space-time that expands outward from an initial extreme condition. And if loop quantum gravity suggests that collapse can lead to a bounce, if black holes can, under certain conditions, transition into white holes, then it becomes tempting to ask a much larger question. Could our expanding universe have been born from the ashes of an older contracting space-time? Could the Big Bang have been, in some deeper description, a big bounce? It sounds impossible when you first hear it, and yet within some quantum gravity frameworks, it is not only imaginable, it is allowed. We don't have definitive evidence. We don't have a single agreed-upon theory. But the possibility itself is a reminder of what black holes keep doing to us. They pull on the edges of our certainty, and they make the universe feel wider than the stories we learn to tell ourselves. And perhaps that is the most honest place to leave it. Not with a hard conclusion, but with a quiet aftertaste. An invitation to let your mind drift for a moment in the strange curvature of space-time, where endings can look like beginnings, where shadows can look like substance, and where the universe may still be keeping some of its most beautiful structures just out of reach. If you're still awake, you can continue to the next chapter. Otherwise, I hope you sleep deeply and dream gently. Good night.